Okay, so we're going to talk about probability and some of the basics of probability. Now, as we discuss things, we're going to go through 3 different means by which you can calculate or at least estimate the probability that something will happen. The probability really represents the likelihood of an event. Now, in order to help calculate these things, we need some vocabulary, and we're going to start building that up with the idea of an event. The event is a collection of the results or outcomes from an experiment or procedure. So that could be like tossing a die, flipping a coin, generating a random number, etc. But you're doing something to generate a collection of possibilities. And that collection, or any member of that collection, is an event. Now, some of those events are so-called compound events, and some of them are more simple. For instance, if you're rolling a die, you could roll an even number, a 2, 4, or 6. That's a compound event because it's made up of a 2, a 4, and a 6. A simple event would be something like rolling a 3 or rolling a 4. Those are simple events because you can't break it down into smaller events. And the collection of all these simple events is called your sample space. It's a collection of all the simple events that can happen from your experiment or procedure. Now we need some notation to describe these things. And it's going to start out with P for denoting a probability. But the probability of what? Well, A, B, or C. These are going to be specific events. So, for instance, a lot of times I'll take, just write down like a letter, probably of an H, or maybe I'll actually write it out, probability of the heads. But if I was to toss a fair coin, what's the probability that I'll get a head? What's the chance that I'll get a head flipping a coin?
1 out of 2.
50-50.
Yeah, 1 out of 2, a 50-50 chance, 0.5, 50%. A lot of different ways you can say that. So, okay, nice. So that's an example of this notation, the probability of this event. And there's your probability. Now there's 3 ways to calculate these probabilities. Now you just did what's called the classic approach. Well, let me talk about all 3, kind of in the order which they were covered historically. Now, one way you can come up with probabilities is the way they used to have to do this before such noted mathematicians as Blaise Pascal actually sat down some formal rules. And the way they used to do it is they used to do a lot of experiments and just keep track of the outcomes. So you roll a die 6,000 times, and you find out that, oh, about 1,000 times you came up with, actually I should say a pair of dice. You roll a pair of dice 6,000 times, and about 1,000 times it comes up with a 7. So you might just start to think that, well, 1,000 divided by 6,000, about 1/6 of the time you're going to roll a 7 with your pair of dice. And that would be a relative frequency approach to probability. So that's one way of approximating probability. And sometimes that's all you can do. It's going to depend on the circumstance. Now your classic approach is what we just did here. The number of ways that something can occur divided by the total number of simple events. So there's 2 sides to a coin, only one of them is a head. So there's your probability. Now there's one more possibility in terms of coming up with probabilities, and these are subjective probabilities. And these are based on your knowledge or your experience, just your rough guess. What do you think the probability is? Now going back to this part right here, this kind of gives us some insight into some bounds for probability, the minimum and maximum. Now the number of ways that an event can occur, what's the smallest number do you think that could be? What do you think the smallest number is that I could put up top? What if something can occur? Then the number of ways that it could occur would be 0.
1.
0. Something might not be able to occur at all. In which case you have 0 over n, which is just going to be 0. Now, on the other extreme, something could always occur. In which case its probability would be, well, this s would be an n over n would be 1. And so your possible values for probabilities fall into this category between 0 and 1. So probabilities are between 0 and 1. And let's discuss what each of these means. What is a probability of 0 going to mean? Something has a probability of 0, what's that mean?
It's not
It's
going to happen.
impossible to happen.
Yeah, it can't happen. It's impossible. It won't happen. So what's the probability of 1?
That it'll happen 100%.
Yeah, it will happen. There's a 100% chance that it will happen. Now, probabilities are stuck in this range. So please don't give me, say, 110% or a negative number or anything outside of the range of 0 to 1. Keep your probabilities here, and I'll keep your credit to somewhere between partial and full, all right? But if you give me something outside of this, I'll be tempted to take off extra points, bonus points. So you lose 6 points on a 4-point problem. It just can't happen. And I'm being a little bit facetious here. I wouldn't take off extra points, but I've always been tempted. You can't have values outside of this range. Uh-oh. Uh-oh. This is blanking out here. That's not good. All right, so let me see what's going on with that for a second. And let's talk about some things with probability of 1. What's something that has a probability of 1? There's 2 things that are usually said to go together that have probabilities of 1. Does anyone know what they are? Death and taxes. Death and taxes each have a probability of 1. You're not going to escape either one, right? It's a little bit cynical, a little bit funny, but death and taxes have a probability of 1. Let's look at the other extreme of our probability spectrum. Between 0 and 1, you have various degrees of likelihood or unlikelihood. And here's where I'm going to call on you guys to come up with something here. I'm not sure if it's in this class or in another class, but I think I've got a Lions fan someplace in my classes. So let's take a look at the probability that the Lions win the Super Bowl.
That going to be up there with death and taxes, that it won't happen?
Probability that they win it or don't win it. Which one?
That they don't even make it to the Super Bowl.
They don't even make it. So probability that they win it would be
0.
Yeah, 0. All right.
I don't know. It's 2020. Anything could happen at this point.
Well, I think the way things started out last Sunday, 2020 has proved that COVID has not affected the Lions. That's all I can say. All right. Yeah, let's take a look here in the chat. Yeah. So, but you know, with all due respect to the Lions, they're going to be the pallbearers for me at my funeral. That way they can let me down one last time. All right. Don't forget to tip your servers. I'll be here all week. All right. Let me see if my webcam's up and running again. It just blinked out for some reason. I'm not sure what's wrong with that. We'll give it another shot here. Hold my, oh, phew. There we go. So probability of death and taxes, probability of the Lions win the Super Bowl. And then you got all kinds of uncertainties in between. Let's do a subjective one. So this one's problem number 4 from the book. And basically it's a probability that a light bulb works the next time you try it. Now, I'm not sure if there's a way that you could actually calculate this. Maybe there is, but it's more or less a subjective probability that we're looking for here. What would you say about that probability?
Likely.
99.
Yeah, I'd say at least 99. Now, somebody said 0.9 in my morning class. You know, and I can get it, 0.9. But really what that's saying is that 90% of the time it's going to work, or 10% of the time it's not going to work. I don't know. Does 10% failure rate sound accurate? So yeah, I like 99 better. So that means 99 times out of 100, you're going to go to that light switch and it's going to turn on. In fact, maybe even 0.999, because they almost always work, right? I mean, it goes months or years before you have to replace one, especially if you've got a good LED bulb. So yeah, something high is what I'm looking for here, something pretty close to 1. But should I just put 1 there itself?
Nope.
No, because at some point it's going to fail, right? Some point it's subject to the same thing that just about everything is. So yeah, should be close to 1, but not exactly 1. Okay. Questions on that one? Let's do a few more from the book. Let me go back to the book. The problems in this part of the homework come from page 143. So let me pull that one up here. 143. Here we go. Now again, we're going to use subjectivity. It says use subjective judgment to describe the given number of girls as significantly low, significantly high, or neither significantly low nor significantly high. Now we're assuming that we're going to look at 50 births selected at random from Royal Oak Beaumont Hospital, and in problem number 10, you get 26 girls amongst those 50 babies. Is that an unusual result? Or is that neither significantly high nor significantly low? What would you guess? This is a little bit subjective here, but I'm hoping that you could guess this. How many girls, I mean, in a perfect world, how many boys and girls would you expect out of 50 babies?
25 each.
25 each. Is 26 really high? Or is it kind of like, okay, so you got 26. Yeah, a little variation there.
Neither significantly low or high.
Thank you, Jess. It's neither high nor low. It's close to what you expect. And of course, you expect some variation. How about if you, in problem 12, got only 5 girls? How would that look for you?
It would be pretty low.
Yeah, that'd be really low. All right. In fact, I'm kind of curious here as to exactly how low that would be. And we'll be able to figure that out for ourselves pretty soon. But the probability of that is really low. It would start out with 8 zeros and then a 2. So if you got 5 girls out of 50 babies, there's something going on, because that's unnaturally low. So for this one to be significantly low. It's much less than you would expect. Now, we do have kind of a formal cutoff for these kind of events. And let me see if I can't find that.
Bless you.
Thank you. So significantly high and significantly low events. These are events that happen when your number of successes, the probability of X or more successes is less than 5%. Or the probability of X or few successes is, again, less than 5%. And let me highlight that a little bit here for us. So this part right here. So your events has a significantly high number of success, and I want to stress significantly high number of successes if the probability of that many successes or more is less than 5%. And conversely, significantly low number of successes if the probability of X or fewer, so like in our case with problem number 12, 5 or fewer is less than 5%. So that's what we're going to rely on a lot. And it's also going to refer back to something called the rare event rule for inferential statistics. And basically what it's saying is that there's two possibilities. Let me go back to the example that we're looking at in the text. The probability of getting 5 or fewer girls, assuming that each boy or each baby has a 50% chance of being a girl, that probability is really, really small. So either, if this happened, either we observe something which is rare, or our assumption that girls have a 50-50 chance of being born is wrong. One of those two things. So at this point, you know, if we got such a really low probability, I'd probably ditch the hypothesis that girls have an equal chance of being born as boys. That's what they're saying. Okay, we don't have to worry about that part now. That's going to become more relevant when we work with hypothesis testing. Let's stick with some probabilities. And the next one I want to look at is going to be problem number 16. A lot of times when we're working with problem number 16, I got to caution people that it's okay to have a problem that's not super, super hard from time to time. Based on a report in Neurology magazine, 29.2% of survey respondents have sleepwalked. Wow. Not sure who's responding to Neurology magazine, but in all the years I've been teaching, I've only had a handful or less of people who have actually experienced sleepwalking. But okay, let's say it's closer to 3 out of 10. The problem is asking you to express the indicated degree of likelihood as a probability value between 0 and 1. So what's that as a probability between 0 and 1?
Would it be 0.29?
Yeah. Yeah, let me also put in the 2 there, 0.292. Yeah, all you're doing is you're moving the decimal 2 places to the left and ditching the percent sign. That's it.
That was easy.
Yeah, there you go. So 0.292. That's all they're looking for in this one. Okay, let's do some more. And this next one's going to involve a table here. So let me show you that table real quick. And that's problem number 22 and 24. So there's your table. And I'm going to copy this table down into my notes. You can start copying it down as well as you like from here. And let's see. Positive. Okay, so here's what it's starting to look like. You're subjecting certain applicants to a drug test, and there's a couple possibilities. Either the subject uses drugs or subject does not use drugs. Subject doesn't use. Now, of the subjects who used drugs and got a positive test, there was 45 of them. Of the subjects that used drugs and didn't test positive, there were 5 of them. So you got 5 negative results amongst the users. Of the subjects who didn't use the test, 25 of them had a positive score, and 480 had a negative score. Now, of the 4 cells in this table, 2 of them are correct results. Which 2? Which 2 cells represent correct results?
The subjects that use, they have the 45 and the 5.
Good. So these subjects here, those 45 people got a positive result and they actually use. So these are your true positives. True positive. Where's the other correct result? Just give me the number that corresponds to it.
480.
480, good. And these are true negatives. All right, so they don't use and they tested negative. That's what you want to see. Now, these people had false negatives, and these people had false positives. Now, each one of these false ones presents a unique challenge. And let's start out with the probability of a false positive. Now, to come up with the probability of a false positive, let me throw in some marginal totals: 70, 485, 50, 505. And notice that both of these totals, either way, total up to 555. Okay. What's the probability of a false positive? You're choosing a tape, you're choosing somebody at random from this. What's the probability that they were a false positive?
25 over
25.
5. Sorry, go ahead.
25 over.
Yeah, 555, right?
Nice, well done. Now, what I typically ask when I do this is, what's wrong with an answer of just 25? How come I can't just say 25?
Because that could be 25 out of 50 million.
Okay, good. Well, what else? What did I warn you about earlier?
Rounding.
Probabilities are between 0 and 1. 25 is not between 0 and 1. So, got to be careful. And you guys nailed it. You guys nailed it right off the bat. 25 out of 555. So, all right, that's a little bit less than 5%, which doesn't sound too bad. I guess it depends on how big of a population you're applying it to, you know, and what are the consequences of this? Let's put it into today's perspective. If these were false positives in terms of the coronavirus test, which has been given to millions, 5%, that's 50,000. Wow. All of a sudden, that's a lot of people. Is it 50,000 or 5,000? 5%. 5. Yeah. What is it? 50? Now I'm not sure. Now I'm doubting myself. I think it's 50,000. 0.05 times.
It's 50,000.
Did you say out of
Yeah.
50 million?
No, it's 50,000. So it'd be 50,000 out of a million. So wow, that's a lot of false positives. You're going to send a lot of people home worried that, oh my gosh, I got the coronavirus. How about the probability of a false negative? Let's extend this one. Probability of false negative.
5 out of. Go ahead. Sorry.
No, you're both good. 5 out of 555, right? So now you're talking about less than a 1% false negative rate, which, you know, again, putting it in the context of the coronavirus, all right, that's not too bad. Of these two, if you're applying this to the coronavirus, which one would you want lower, the false positives or the false negatives? I guess you got to think about which one does the more damage. Telling somebody that they do have it when they don't, or telling somebody they don't have it when they do. Which one's worse?
Telling someone they don't when they do.
Yeah, the false positive.
False positives? So here you're making somebody worry unnecessarily. Here, you're saying, yeah, go out and circulate, you don't have the virus. Both of them are bad. Personally, I guess I think this one is worse because then you're keeping that person in circulation when they shouldn't be. So, all right. So kind of a good one to argue about. Maybe there's some philosophical differences there, but those are the two probabilities involved. Are we okay with the calculation of the probabilities?
Yes.
Yep.
Thank you. Let's look at the next one, problem number 24. Find the probability of selecting someone who does not use drugs. All right, so let's just stop there. Probability of selecting somebody who does not use drugs. Probability doesn't use.
So 505 over out of 555.
Nice. Now notice what's different about this one. Instead of looking at one of the individual cells, we had to look at the entire total. There's 505 people out of this survey that don't use drugs. So 505 out of 555. So I'm guessing around 90% there, somewhere there, but that's the right numbers. So are we okay with those two calculations?
Yep.
Okay.
Yep.
Thank you. All right, let me continue. Do maybe one more and then take a break. Let's take a look at problem number 30. So we'll go back here. And then the next page, I'm hoping the next page has problem 30. Yes, I got lucky. So car rollovers. So in a recent year in the United States, 83,600 passenger cars rolled over when they crashed, and 5,127,400 passenger cars did not roll over when they crashed. So, question is, find the probability that a randomly selected passenger car crash results in a rollover. Is it unlikely for a car to roll over in a crash? So, let's look at that one. And so we'll call this probability of a rollover. There was 83,600 rollover crashes. And there was 5,127,400 that didn't roll over when they crashed. Is that enough? Is that what I want to calculate for my probability?
Yes.
Well, if we go back to that PowerPoint that I looked at earlier, when we calculate things this way, we've got to calculate the number of ways that an event can occur, which for us in this case is the 83,600 that occur over the number of different simple events. And here in the denominator, we're lacking a little bit. These are the number that didn't crash. We've also got to add in the number that did crash to get the total number of car accidents under investigation. So in this case, that turns out to be 83,600 divided by, let's see, if we add that, that's going to be 5,211. So 5.211 million. So 0.016 ... or about 1.6%. So quick question here. Is it very likely that you're going to experience a rollover if you're in a crash?
No.
No. It tends to be on the unusual side for that. All right. Okay. So we're going to finish up this section with some work on odds. Now, our work on odds is going to entail the ratio of a couple of probabilities, the probability that something actually happens versus the probability that it doesn't. Now, you can form this ratio, but usually it's expressed in the form of A to B. So let's take an example of this. And for that, let's see. No, here we go. It says, in a certain study, the chances of encountering a crash on the road are stated as 5 in 17. Express the indicated degree of likelihood as a probability value between 1 and 17. And then we're going to go and express it as a set of odds, the odds of having or encountering a car crash. So let's take a look at that. So starting out with the probability, chances are encountering a car crash are 5 in 17. So I'll call this maybe example. Yeah, by now we're probably on example E or something like that. Call it example E. 5 in 17 is your probability of a crash. It's like that, 5 in 17. Well, let's understand that probability a little bit more. Of these 17, 5 of them are crashes and 12 of them are not. So the odds of encountering a car crash, odds of a crash, are 5:12. 5 times it'll happen, 12 times it won't. Okay. Let's take a look at another one like that, except going a little bit deeper. And that one again is on your handout. We're going to look at a modified slot wheel, roulette wheel, I should say. And for those of you not familiar with the roulette, let me pull up a roulette wheel for us. Let's see, is it here? Yeah, there we go. So a roulette wheel is something you're going to use in gambling, and it's going to have a bunch of numbers, 1 through whatever. In this case, and in most cases, 1 through 36. And those numbers are going to be colored either red or black, but there's 1 or 2 instances of something else. And in this case, there's only 1. There's a 0. And now the 0 is colored green, doesn't count as red or black, doesn't count as odd, or even it's just 0. Now in our example, our modified roulette wheel has 2 slots, one that's 0 and one that's double 0. And the remaining 42 slots are numbered 1 through 42. And we're going to use this modified roulette wheel to calculate some probabilities. So we're going to start with the probability of winning. So call this example F. Probability of winning well, I'll help out here a little bit. There's 44 slots in our wheel. So that's going to be our denominator. Now for our numerator, we have to decide how many, let's see, we're going to bet on how many even numbers are there amongst those first 42 numbers. How many even numbers are there in the first 42 numbers?
21.
21, because every other one or half of them are even. So our probability of winning is going to be 21 out of 44. Okay, and that's it. That's all there is to that one. It's just a matter of understanding the problem a little bit and counting up how many ways there are to win divided by the total number of possible outcomes. We're okay with this part. Okay. What are the actual odds against winning? So we're going to do here what we did with our previous one. We're going to break up that probability into 2 pieces. So there was 21 ways you can win. How many ways are there that you can lose?
23.
23. So for our part B here, the odds against winning will be the number of ways that you can lose. 23 colon 21. Number of ways you can lose against the number of ways you can win. We did kind of the opposite up here. The number of ways you can encounter a car crash versus the number of ways you could fail to encounter a car crash. So that's your odds against winning. So, okay. A little bit more likely that you're going to lose versus that you're going to win. Let's keep going. When you bet, the outcome is an even number. The payoff odds are 1 to 1, meaning for the payoff odds, that's telling you how much you win versus how much you bet. So if you bet $1, you win $1. That's what the payoff odds are telling you. And let's see, do I have that written down in part of our PowerPoints? Payoff odds. Yeah, here you go. Your net profit versus the amount that you bet. So you profit $1 when you bet $1. So if the payoff odds are 1-to-1 and you make a $14 bet, how much you're going to win?
14 odds.
Yeah. If odds are 1-to-1. So if you bet 14, you win 14. Nice.
Wouldn't you make twice the amount that you bet though originally because you profit 14?
That's a great question. And your answer is readily provided in the words you used to ask the question. You profit. So they're going to hand you back $28, but your net profit is the $14 above what you gave them as your bet. So it's your net profit compared to the amount that you bet. Does that answer your question?
Yeah, thank you.
Oh, good observation, though. Very, very sharp on that. Now, let's say that you could convince the casino they should really pay you not the payoff odds, but the actual odds against winning. Now, those actual odds against winning are something we just calculated, and they were 23-21. So let me go back here, 23-21. 23-21. And to understand that a little bit better, let me divide each side by 21. And that would mean that for every dollar we bet, 23 divided by 21, I think it's about $1.09. Let me just check that. 23 divided by 21. How about this? 23 divided by 21. Yeah, about 1.095. So 1.095. So for every dollar you bet, you should get a little bit more than $1 back, almost $1.10. That's how much you should get compared to your actual risk in betting $1. So if you're going to bet $14, if I'm going to bet $14, if I times this by 14, bet 14, then this times 14 should tell me how much I should win. So I'll take that and times it by 14, and I should win $15.33 if I round it off right. So 15.33. That's how much I should win if they're actually paying me the right way. Now, this difference between the payoff odds and the true odds is the house's advantage on you. And it's, this is not something I'll test you on, but if you ever wanted to look into this more carefully, if you cared about keeping track of your money when you're gambling, you'd want to look up something called the vigorish, or just better yet, the VIG. That's the house's advantage on you. And this is almost a 10% advantage. That's pretty crappy. That's really crappy. If you play your cards right, there's certain games in Vegas where you can get that advantage down to less than 0.5%. So, wow, that's a striking difference between here and here. I wouldn't play this game, ever. It's just not worth it in the long run. You're going to stay there in the long run, learn to find this game, all right? But it's not my job here to teach you how to gamble, just other than to say, hey, a fool and their money are soon parted. There's smart bets you can make when you're gambling, and if you're going to risk your money, do it wisely. But back to the statistics part. Are we okay here?
Yep.
All right, thank you. Let's try one more kind of like that, working with odds and things. And let's see. I think that's at the bottom of your handout. I still have one more like this. Ah, yes, the Kentucky Derby. All right, so cool. Let's talk about this. course, if you're going to go down there, you probably want to maybe put a few bucks on something just so you can enjoy the race a little bit more. So, when the horse California Chrome won the 140th Kentucky Derby, a $2 bet on California Chrome resulted in a winning ticket worth $7. So, part A says, how much was the net profit from the $2 bet on California Chrome? So you bet $2 and you got back $7. What was the net profit? Aiden?
5.
All right, Amber, $5 was the net profit. Cool. So what were the payoff odds against California Chrome to win? What were those payoff odds? Well,
5-2.
5-2. Yeah. You have $5 for every $2 that were bet. So 5-2. Those are the payoff odds against him winning. Now, let's look at the next one. According to the pre-race wagering, bettors collectively believe that California Chrome had a 0.228 probability of winning. So let's look at that, and let me help you out with that. Probability of winning was 0.228. Let me think of that as in a different way. That's 228 over 1,000. Now let's break this up. Remember how we broke it up earlier? We've done 2 examples like this, and we'll call this one example G. But in examples E and F, we did this twice. What do you think I should do with the denominator? How should I rewrite it?
Subtract 228 from 1,000.
Good. So 228, and subtracting that from 1,000 is going to give me, what, 772?
Mm-hmm.
So this is the ways to win. This is the ways to lose. So if I want the odds against winning, let's just double check that that's what they're looking for in part C. What were the actual odds against his winning? So odds against his winning would be the number of ways that he could lose versus the number of ways to win. So odds against winning. So that'd be the number of ways to lose, number of ways to win. So 772 to 228. That's our answer for part C here. Are we okay with that one?
Yep.
Yeah, so pretty much whenever it says against like the odds or whatever, you want to divide up the number.
Yeah,
or
you divide out the probability. Now, we could also look at the odds for winning. Can anyone think what those would be?
Just flip it.
Yeah, just flip it. 228 to 772. Those are the odds for winning. Just flipping it around. Thank you. Now, the last part, we're going to work with this and say, all right, how much would your $2 bet be worth if they actually paid you the true odds against winning. Because remember, the odds that they gave you were 5-2. They paid you $5 for every $2 you bet. But what would that look like if they paid you off according to the actual odds, the true odds against winning? So do you remember what we just did a moment ago?
Divide the 228.
Divide
the
by
7.
228.
Yep.
So I'm going to divide each of those by 228. And on the one side, I'm going to get $1. And the other side, I'm going to get something like 3.4, 3.5.
3.385.
Thank you. 772 divided by 228. So it's telling me for every dollar bet, I should win back $3.38, 39 cents. There we go. So 3,386, we'll call it. Except I had a $2 bet, not a $1 bet. So if I multiply this by 2, I'll just do that on my calculator. That $2 bet should have resulted in a profit of $6.77 for me. So 6.772 for a $2 bet. And that's your answer. That's how much money you should have collected if they were paying you the true odds. Of course, they can't. They got to pay the concessionaires and other people working there. They got to pay the state, et cetera, like that. So a lot of that money gets siphoned off for other things. But the difference between this and the $5 is the profit that goes to the racetrack and then the states and stuff like that. All right. All done with that one. How are we looking there?
Good.
Okay,
Pretty good.
cool. Pretty good. If there's some questions here you want to ask in follow-up, now is a good time. All righty. Well, we'll stop it here then.